Hey guys, it's Sean with Alexander Tutoring. It's time for your daily dose of relativity, day 4. So last time I asked you if we are all to arrive at class, at a classroom at 8 a.m., how do we all arrive at the same time? So the point is this. We all need to arrive at roughly the same point, the classroom, or an XYZ coordinate if you're a math person. And we all have to do it right when our clock hits 8. The hands on the clock hit 8. And so what I'm arguing is in order to have a proper definition of time that works, what we are actually saying is that our arrival at the classroom is simultaneous or coincides with our rotating clock arriving at the 8 o'clock position. So what I want you to notice is that we can't say anything about time without defining relative motions. That is, we have the relative motion of our clock and the relative motion of you going to class. And what we do is you happen to arrive at class, boom, right when the clock simultaneously hits the 8 o'clock position. So we are comparing your motion to the clock's motion, and then because we all agree on the same rate of rotation of clock, we're all using the same reference frame or the same rate to judge. We are trying to be at this location simultaneous with this motion arriving at the 8 o'clock position. So sometimes I think it's good to talk to the man himself, this guy. So what I have here is his original 1905 paper on special relativity, the first time he published it, on the electrodynamics of moving bodies by A. Einstein, 1905. This was his first paper on this, introducing the subject to the world. Let's hear what he has to say about it. Okay, well, listen up. If we wish to describe the motion of a material point, in this case us, we can be considered, I am the material point going to class. If we wish to describe the motion of a material point, we give the values of its coordinates as a function of the time. Okay, so that's, our coordinates are the XYZ coordinate, right? So we say if we're moving, we have to say we're at this XYZ location at this time number. We give the values of its coordinates, that's me going to class, as functions of the time. Now we must bear carefully in mind that a mathematical description of this kind has no physical meaning unless we are quite clear as to what we understand by time. We have to take into account that all our judgments in which time plays a part are always judgments of simultaneous events. If, for instance, I say that the train arrives here at 7 o'clock, I mean something like this. The pointing of the small hand of my watch to 7 and the arrival of the train are simultaneous events. So, as we move forward, what we need is an actual physical definition of time to work with that can be measured. And so what we can measure is the simultaneous events of two different moving objects. So case 1 is me, I'm a moving object going to class. Case 2 is the clock rotating. And then me and you and everyone else arriving at class at 8 a.m. is a simultaneous event. Your location is simultaneous with this rotating thing's position. Okay? So going forward, when we think about time, we're going to describe it as two simultaneous events, comparing one motion to another. Got it? Okay, so that's what we're going to do going forward. Thanks for listening. Bye.